This is a beginner's guide to topology. In this video, we are going to take a complete approach in learning topology. We are also going to learn the fundamental concepts, the different shapes, the different surfaces, how these surfaces are related to each other, what is the underlying concept, what are the mathematics, and most importantly, a very brief yet a fascinating history on the development of topology and who are the contributors to this wonderful subject. As far as the mathematics is concerned, I am keeping it brief and I am making it very simple because the target of this video is the beginners. So we would be learning the basic concepts, the fundamental areas of topology, so that in future when you go ahead and do complex calculations, things will become easier. The target is to give you a basic conceptual development on the subject of topology. My name is Shaunak and you're watching this video on my channel Physics for Student. I welcome you to watch this video. So before we go ahead and delve deep into the subject, let us look what are the topics that we are covering. So we are covering basically what is a topology, what is a genus, what is orientability and non-orientability, what are the different branches of topology, a brief history, how topology emerged, what is called a topological invariant, what is the process of generalization, and how do we move from Euclidean axiom to topological axioms. This is the basic topics, but within this topic there are several subtopics and many other concepts are being covered. So I would request the viewers to stay tuned and watch the video till the end. So first we start with the basic idea that what is topology all about. Now, topology is a branch of mathematics which is concerned with the properties of a geometric object that are preserved under continuous deformations such as stretching, twisting, crumpling and bending. So it is derived from the Greek word this one, which means place, and this is location, which also means logy, means subject. So in together, topo plus logy means it is a kind of a place and location to study the subject. The topology studies properties of spaces that are invariant under any continuous deformation. It is sometimes called rubber sheet geometry because the objects can be stretched and contracted like rubber, but it cannot be broken. Right. So as you see on your screen that I have written that is topology studies properties of spaces that are invariant under any continuous deformation. This is the key, that how can, in spite of things being bent or changed, things are getting invariant, and it is helping us for further calculations. So in this video, we will focus on this invariant concept because that is the key, as I have written in red, that topology studies properties of spaces that does not change if they're distorted, wrapped or twisted. So that we are going to find out in due course of time. Okay, so what does it mean that these objects which can be stretched or deformed, for example, if this is a square and this can be stretched or deformed into a circle, but the circle and the further it cannot be twisted or deformed to make a figure eight shape. This is called a figure eight shape, so it cannot be done. So a typical classical example, as you see that from the coffee cup things move to a donut. So I have just made the right arrow to signify that from coffee cup you are moving and deforming into a donut, and similarly from donut you can come back to coffee cup. So the basic idea of giving this is that I will show it in a separate video kind of a workshop using clay models, how these things can be deformed, but it cannot be torn apart, it cannot be glued, but these shapes and objects can be deformed into certain areas, but it cannot be deformed into certain other things, for example in this case a figure eight. So this is basically the essence and idea of topology. So I will just show you quickly some of the objects so that it becomes clear when we are talking of topology what are the objects. So we have got a Klein bottle, we will learn about Klein bottle and Mobius strip, don't worry. Ball, a bowl and a cup, a donut, a torus, triangle, and circle. These are all different topological shapes, but each of these shapes have a lot of underlying meaning, the mathematics, the surfaces, the curves, etc., which we will learn in due course of time. However, some of these objects we are covering in this video. So topology is the area of mathematics describes that objects that remain unchanged, which are called invariant properties. So if I may show you that, for example, if this is a circle and if it is equal to a square, which can be equal to a kind of a rectangle. So I can say that a circle is topologically equivalent to a square, which is equivalent to a rectangle, but mind it is geometrically different. That means that we make a marked difference between what is a geometric notion and what is a topological notion. Because these things which I have just shown you, a circle and a square and a rectangle, they are topologically equivalent, how we will soon see, but remember we cannot call it geometrically equivalent because geometrically they are different. So if I take a kind of a random surface, I mean to say just like a kind of a random object, say for example this blue one, and let us suppose there is a property. What is the property? We are not going to define, we will take the example. So we define a property here. That means that the property, if it remains unchanged, can be equal to the property which is same here, and it be equal to the property as same here. So this is just a kind of an underlying understanding that the area of mathematics that we are dealing about deals with objects that remain unchanged and that are allowed to bend. So the properties which will be lying on any kind of a surface, whether it is square or anything, that must be equal to the same surface, so on. But remember that they can be topologically equivalent, but geometrically they are different. Okay, now we come to a very fundamental and the old concept of topology. I mean to say the topological invariant started. It is called a genus. Now actually, if you talk of genus in general in dictionary, it is a taxonomic rank used in the biological classification of living and fossil organisms as well as viruses. In the hierarchy of biological classification, genus comes above species and below family. So genus in general, it is used in biology. However, here in mathematics, genus or plural genera has a few different but closely related meanings. Let us understand for this time that genus actually means that the number of punctures or hole that we do on a surface. So now the genus of a surface gives back a value which is an integer, and it represents how many punctures or holes or cuttings it has got. So the genus of a surface is an integer which represents the maximum number of cuttings. Most importantly, the genus is a topological invariant of surfaces and it is completely invariant. So let us look into what are the visual aspect of genus. So a sphere, because it has got no holes, it has got genus 0, it has got genus 1, genus 2 and genus 3 and so on. So the number of holes that lies, for the time being, let us understand it is a genus. And most important feature is that two surfaces with different genuses are not homeomorphic. Don't worry if you don't understand the term homeomorphic. We are going to learn very soon in this video. But just let us understand that a sphere or a genus 1 which has got one hole or a genus 3 which has got 3 holes are not homeomorphic. For the time being, let us understand that these are not the same thing. So the genus of a connected orientable surface, as I told you, is an integer representing the maximum number of cuttings, and this is closed simple curves without rendering it is not homeomorphic. Okay. Now once we have learned about genus and we have seen that how it lies, the most important next concept that comes to our mind is that where do those objects lie? Right? We have seen in Klein bottle, we have seen a Mobius strip, we have seen genuses, but where it lies. So that brings us to the next part of our video, which is called orientable and non-orientable surfaces. Now I would like to bring an attention that orientable and non-orientable, these are not right English words in the literary sense, but we can take it as a mathematical word. Okay. So first of all, let us see a torus, right? So orientability in mathematics is a property of some topological places, which is real vector spaces, Euclidean spaces, surfaces, and more generally manifolds that allow a consistent definition of clockwise and counterclockwise. So in this torus, this blue arrow, if an object or a human being moves from this part to this part, and then it moves clockwise and counterclockwise, that means the orientation or the person coming out of that surface will be the same, right? So a space is orientable if such a consistent definition exists. So orientability is a kind of a property which allows consistent definition clockwise or anticlockwise. What does it mean is that if clockwise is changed into counterclockwise after running through these loops, the blue arrows in it, and coming back to the starting point. So here on a sphere, if I go this way and if I go this way, nothing really changes. Same happens with a triangle. So let me just demonstrate it with a torus. Say for example, this is I'm standing on the torus and I start moving in this direction and I move it, and then I start moving in this direction, this blue one, and I start moving here, here, and here. What happens is that nothing really changes. That means it is consistent in terms of clockwise and counterclockwise. That means the movement or the phase coming out of that is not changing, and that is what is called a orientable surface. Okay, further examples, I think it will make it clear. This is what is called a triangulation of a torus. Don't worry, you really don't understand. Now you see the top, bottom, and left and right edges are identified to be the directions indicated by the arrows along the edges. Inside the triangles are curved arrows, right, indicating a clockwise orientation of the triangles. Now a surface is orientable when one moves along a drawing oriented arrow. When one arrives back at the starting point, the oriented arrows we sketched are not reversed. So that is what is important. You see these lines of arrows at the starting point, the oriented arrows we sketched earlier are not reversed. That means the direction is the same. That means if I have got this kind of a pie chart, and if I change this and move it continuously around the surface, it cannot have a mirror shape. That means it is orientable surface. That means the arrows or the people who are moving around the torus I have just shown you, the movement or the orientability is not changed. If clockwise is changed into is not changed into counterclockwise, then it is something which is orientable, which is exactly opposite what happens for a non-orientable surface. Now here is a kind of an animation. If you see that, this is a Mobius strip, right? And the crab which is moving around, see the crab moves here, and then when it comes out of that, right, it has flipped with every complete circulation, right? So the crab moving in a non-orientable surface, it has left and right flipped with complete circulation. So the left, here it goes, and now you see it comes out totally on the right hand side. So the left and right are completely flipped out. So that is what is called a non-orientable surface, but this would not happen in case of a torus. If you have seen the earlier, just a few seconds back, in a torus, if a crab moves, the movement, the left and right is not being flipped. So Klein bottle is also kind of a non-orientable surface. So is the Mobius snail. So remember this, the directrix is reversed when moved around this path. So if I now put this shape and I continuously moved around a non-orientable surface, then it has got a mirror shape. So that is why it is called non-orientable surface. So you see the green and the blue is just taken a mirror shape. So this is a very important concept of topology, that what is orientable, when we move around, nothing really happens, nothing flips. But when I move around the non-orientable surface, Mobius strip, Klein bottle, I have another one is called projective plane. The entire directrix is reversed. So what we can say is that an orientable surface is the one where it moves around along the oriented arrow. It is not reversed, arriving at the point where it is started. That means the directrix is not reversed. Where here with a non-orientable surface, the directrix is reversed. And when one moves along the oriented arrow, it is reversed, arriving at the point where it started. Now, this is a very important concept of topology, orientability and non-orientability of surfaces. Now, this particular orientability and non-orientability, how we calculate it. Now, the question is that how do we do the calculation? What area of topology actually measures that? That is most important in the next part of our video. What are the different branches of topology? So first of all, let us understand that there is something which is called a general topology. Then we have algebraic topology, we have a differential topology, and we have a geometric topology, which is further divided into a low dimension and a high dimension topology. So let us start first of all with the algebraic topology. These are important because otherwise we won't be able, whenever we are doing a measurement of any surface or a manifold, we would be left in dark and we don't know really that which area of topology does the calculation. So algebraic topology is a branch of mathematics that uses tools from abstract algebra to study topological spaces. The basic goal is to find algebraic invariants. Again, the concept of invariant, that is things which doesn't change, that classify topological spaces up to homeomorphism. So although algebraic topology primarily uses algebra to study topological problems, using topology to solve algebraic problem is also possible. So here you see the basic goal is to find algebraic invariants, and I've just given a small note. What is an algebraic invariant? It is a quantity just like a polynomial discriminant which remains unchanged when there is an algebraic transformation. So for example, if we see that the torus on the right hand side and a sphere, so the torus is different from the sphere. Why? Because the torus has a hole and the sphere doesn't, right? Now, however, since the continuity is a basic notion of topology, only deals with local structure. So sometimes it becomes very difficult to formally define the obvious global difference. That means it has got a hole and it has got a sphere. So that is why you see that to find out the difference between torus and a sphere and other objects becomes very difficult. So what we do is that in algebraic geometry we use something which is called homotopy. Now don't worry about those terms. Homotopy is just a group, right, which carries different way to classify the shapes or the topological spaces. So what is this? This one is the first homotopy group. Homotopy means it is just a group. For example, a group which classifies elephant, a group which classifies monkeys, a group which classifies any other object. So this is how we classify the torus. And now you see this is the way we classify sphere. So the first homotopy group of the torus is this one. And the other hand, the sphere S2 satisfies this. So if we use those homotopy groups, that means we are using a classification. We have classified the objects. So a object which has got a one hole will be under category A, which has got a two hole will be under category B, and so on. So homotopy group is a way of classifying those shapes. So the torus and the sphere obviously are, if they are not on the same homotopy group, that means they are not homeomorphic. So for example, if I classify the tuskers, elephants into group as T, and if we sometimes those another kind of an elephant in T1, then if the T and T1 are not giving the values, then obviously the tuskers are not this kind of mammal, this kind of elephant. So homotopy group is just a kind of a classification done in algebraic topology, so that in case we are unable to discriminate between two shapes, this is how we do it. So just to summarize, it becomes difficult to distinguish between things. Showing 3D space are not 4D spaces really becomes difficult, as it might not seem right now. So one of the ways people found to deal with those difficulties is to create something which is called a functor. I'm not going into that. So we create algebraic objects or some numbers, right, that map certain objects into another objects, and algebraic objects like vector spaces and groups. Now, for example, we will show that if this is a shape, right, we show that this shape, or what, for example, a topological space, it gives out or it produces a number. Say, for example, the number is 2. Now, if the second shape also produces another number 2, then we find a conclusion that shape 1 is equals to same 2. Or technically, we can say that if two topological spaces are the same, they will get the same number attached to it. Contrary, if two spaces which are tagged are with different numbers, obviously they won't be the same. So if I get a shape 2 again, then it would be difficult, same, but it won't be that of shape 2 because the shape 2 gives a number which is 10. So from here what we can tell is that these shapes are then classified into different groups which we call homotopy or otherwise, which studies their shapes, holes and structures. And algebraic topology helps to classify different shapes, how different a coffee mug is from a baseball or any other objects, right? So algebraic topology is a way of categorizing the shapes, and once we assign a number, and if the same number is being produced by the next object, we can deduce that one shape is similar to other. So from here what we can say that if we want to study two closed loops, say for example these loops of different shapes and sizes, right? So they are topologically distinct only if they cannot be transformed into each other, as we read into continuous deformation. Now in the case of knot theory, this might involve, for example, a map, and we assign a unique integer to any given closed loop. Such a map can be very useful if we can show that it always assigns the same integer from one to another that can be continuously deformed. That is, topologically equivalent loops are assigned the same number. If, for example, if you are given two closed loops that are mapped to different integers, obviously then this instantly says that they are topologically not same to each other. So if you are starting knots, in case of a knot theory, I'm not going into that. Algebraic topology is a way of studying these structures by translating them into algebraic properties, assigning a value, and if they are equivalent, fine, otherwise not. Quite simple. What is an algebraic topology? And next what we come is what is called differential topology. So differential topology is the field dealing with topological properties of smooth properties or smooth manifolds. Now, I would like to take a pause and tell to the viewers that if you really want to know more about smooth manifold, just a few days back I have posted a video which is called Introduction to Differential Geometry, where I have spoken at length about smooth manifolds, invariant, diffeomorphism, all those. So if you really want to understand the technical terms taking into diffeomorphism and smooth manifolds, it is there in my playlist in differential geometry. So the latest video is what deals with that. So it deals with properties and invariants of smooth manifolds that are carried over by diffeomorphisms. So that means what do I mean by diffeomorphism? Just given an idea from my last video, something which looks like locally Euclidean. So by comparison, differential topology is concerned with coarser properties such as the number of holes in a manifold, its homotopy type, or the structure in the diffeomorphism group. Because many of these coarser properties may be captured algebraically, differential topology also has a strong link with algebraic topology. So here you can see right at the bottom of the screen, it is a global aspect where people are moving. When we map it to something very local, that is in general, very broadly, although it would be wrong, it is what is called diffeomorphism. And smooth manifolds means a manifold which can be differentiated infinitely. So in general, what we mean is that differential topology deals with topological properties which have got smooth manifolds and which are invariant under diffeomorphism. You want to understand about diffeomorphism? Please go to my recent video on differential geometry. In my playlist, you will understand. Now, obviously, when we talk of differential topology, there comes a distinction that what is differential topology and what is differential geometry. Just a quick look. Now, see, one major difference basically lies in the nature of the problems that we deal with, right? So, differential topology distinguishes itself from differential geometry by studying primarily those problems that are inherently global. So obviously topology, as I have earlier discussed, deals with global. Consider, for example, the differential geometry studies primarily those are very local. Now, for example, the coffee cup, this animation. So from the point of view of a differential topology, the donut and the coffee cup are the same in some sense, right? This is an inherently global view. So because there is no way the differential topologist to tell whether the two objects are the same by looking at just a tiny local piece of either of them. They must have access to the entire global subject. So donut and coffee are the same for differential topology, and here it comes to be different. So from the point of view of differential geometry, the coffee cup and the donut are different because it is impossible to rotate the coffee cup in such a way that its configuration matches with that of the donut. This is a global way of thinking about the problem, but an important distinction is that the geometer does not need the entire object to decide. Just by looking at the coffee cup or just of the piece of the handle, they can decide that the coffee mug is different from that of the donut. So it studies basically manifold which are global, it studies manifold which are local. So in just a way, just to tell you that differential topology or topology as a whole, it deals with global aspect, here it deals with local aspect. The donut and coffee cup to their topologies, they are the same, and here they are the different because differential topology deals with local structures such as by holding the coffee cup in hand, they can find out there's a hole, something at which the donut doesn't have, so they call it different. Okay, so we come to another important aspect which is called geometric topology. Now, geometric topology actually is a study of manifolds and maps between them. So here, as you see, in order to, what happens is that when we are taking manifolds and studies into further aspects, it sometimes become very difficult to measure them. So it is a sub-branch of topology that studies manifolds and maps between them. So it uses the sub-branch techniques like cobordism, surgery, algebraic variants. Let us not go much details into this. So because I would say in some way the manifolds behave differently when the manifolds are measured in different dimensions. So we have divided geometric topology into two parts. The lower dimensional topology, which deals with 2, 3 and 4 dimensions, knot and braid theory, surfaces, hyperbolic 3 manifolds, exotic R4 and so on. And higher dimensional topology actually deals with 5 dimensions, embedding in co-dimensions 3 and above. So it is kind of immersion or putting that kind of a object into higher dimensions and so on. So just to summarize, geometric topology deals with manifolds on higher dimension, and it is divided into two parts. The lower dimension, as you can see, covers these areas, and higher dimension all those areas. Now, when we are talking about those knot and braid theory, exotic R4, 5 dimension, can we visualize them? Is there any way we can just see them and we can get an idea? That is what I'm going to show you right now in this part of the video. So if I talk of one-dimensional manifold, it is basically a long line or a circle or a real projective plane and a real line. So this you can just imagine as a one-dimensional manifold. Two-dimensional objects are mostly cylinder, it's a Klein bottle, a Klein quadric, Mobius strip and sphere and so on. In details, each of these objects and their history and details I have dealt in a separate video of differential geometry. You can have a look onto it. This is the two-dimensional manifold. When we talk of the three-dimensional manifold, a three-sphere, a solid torus, and a Whitefield manifold comes into play, which is being discovered by the founder of homomorphic theory, J.H.C. Whitehead. So I'm not just going into much detail, just giving you a glimpse. Four-dimensional manifold, yes, very difficult to display, but here it is. E8 manifold, the Enrique surface, the Del-Pezzo surface, the complex projective plane, and we are just talking about exotic R4 invented by Michael Friedman in 1982. So further four dimensionals are these one, right? Projective plane and this. So what we can say is that geometric topology deals with high dimensional manifold. The behavior of manifolds are sometimes very radical, so we have divided them into lower dimensional, which are those, and higher dimensional are those. And the tools that we use are fundamental group, orientability, local flatness, and Schoenflies theorems. These are too technical. This is not the right time to deal with this. So this is all in all what is called geometric topology. So far so good. We understood the invariance property. We have understood what the topological objects are. We also understood what are the different branches of topology and what these branches really deal about. And we can understand that these are basically to study something invariant in spite of things getting changed. But who are those people who contributed in measurement? Who are those great people who helped our life to become so easy? So let us find it in the next part of the video. But before that, a quick glimpse on what is a general topology. So it is basically the topology that we are going to study. It is a point set topology, the study of the basic concept topology. It deals basically with properties, spaces which are closely related to analysis, and we use set theory to do the calculation, and it is the foundation of different topology and geometric topology and algebraic topology. So the topology I am teaching, or rather the most generic topology which is being dealt, this is general topology. Earlier it was called point set topology, now we call it general topology, and this is the foundation of other topologies. So as you see, these compactness, product spaces and open balls, disconnected paths, metric spaces, topological space, these are the concepts underlying issues, mathematics, etc. Everything related to general topology. And I'm going to cover all this one by one in this series of videos. So general topology, as we have found, is the basic foundation. And now that we have understood almost all the four topologies, now it is time to find out who are the contributors of that. And that we would find out in history of topology. Now, topological ideas are present in almost all areas of today's mathematics. We shall now go to trace the rise of topological concept in a number of different situations. The year was 1736. The city of Königsberg in Prussia was set on both sides of the Pregel River and included two large islands, Kinhof and Loms, which are connected to each other. The problem was to devise a walk through the city that would cross each of these bridges once and only once. Now, in the history of mathematics, Euler's solution of the Königsberg Bridge problem is considered to be the first theorem of graph theory and the first to prove in the theory of network. Euler pointed out that it has got no solution. This is the paper which he wrote. I just got a glimpse of that paper. So Euler pointed out that the choice of route inside each land mass is irrelevant, right? So the only important feature of a route is the sequence of bridges that are crossed. This allowed him to formulate the problem in abstract terms, eliminating all features except the list of land masses and the bridges connected to them. In modern terms, as of today, one replaces each landmass with a vertex or node and each bridge with an abstract connection or edge. This actually resulted in the birth of graph theory as well as topology. This is considered the seven bridge problem, which Euler found out as no solution, is the birth of topology and graph theory. Now, it was during this time Euler wrote a letter to Christian Goldbach because he has identified the importance of the polyhedron. So what he did is that he formulated the famous polyhedron formula right on your screen. So these are the polyhedron surfaces, and if we take a cube which has got 6 faces, 8 vertices and 12 edges, and if we plug in the Euler's formula, then we get what is 2 equals to 2. That means it is proved that cube is a polyhedron. So this is very important. It gave birth to the idea of topology and the polyhedron formula which Euler invented, and we use it widely. Now Simon Anton Jean Laurier, which was born in 1750, was a Swiss mathematician, and he is known for his work in mathematical analysis and topology, and in particular generalization of Euler's formula for planar graph. And it is he who found that Euler's formula was wrong. So if a solid has got certain amount of holes, Euler showed that the formula has to be reformulated as this, and this was first known as on topological invariant. We move to another person, J.B. Listing, who was born in Frankfurt and died in Göttingen. He first introduced the term topology to replace the term geometria situs, also sometimes called analysis situs, a famous article published in 1847. Although he has used the term correspondence in some years, here he first introduced the term topology. He discovered the properties of this half-twisted strip we just saw, and we now know it is a non-orientable surface at the same time as did Mobius, August Ferdinand Mobius, and went further in exploring the properties of the strips with higher order twist. He discovered topological invariants, which came to be known as listing numbers. He also coined in 1872 the term geoid for the idealized geometric surfaces of the figure Earth. We move to 1851, and we find this great gentleman, Bernhard Riemann, contributing significantly to the studies of complex number theory, and he used combinatorial topology as a tool for analyzing functions. And here comes August Ferdinand Mobius. Now Mobius was actually born in electorate of Saxony and was descended on his mother's side from religious reformer Martin Luther. He was homeschooled until he was 13 and studied there graduating in 1809. He then enrolled in the University of Leipzig, where he studied astronomy under the mathematician astronomer Karl Mollwitt. And in 1813, he began to study astronomy under the mathematician Carl Friedrich Gauss of the University of Göttingen. He is best known for this discovery of Mobius strip, a non-orientable two-dimensional surface with only one side embedded in three-dimensional Euclidean space. It was independently discovered by Listing a few months earlier. Mobius configuration formed two mutually inscribed tetrahedra, which is also found in his name. So we find another very important contributor, Christian Felix Klein, a German mathematician and a German mathematical educator, and is known for his work in group theory, complex analysis, non-Euclidean geometry, and most importantly, Klein-Bottle, which is a non-orientable surface. No need to mention this person, Henri Poincaré. Poincaré introduced the concept of homology, and Poincaré introduced the fundamental group of a variety and the very concept of homotopy. So between 1865 and 1973, we find major contribution in terms of topology. Stefan Banach, Polish mathematician who is generally considered as one of the 20th century's most important and influential mathematician. He was the founder of the modern functional analysis, followed by René Fréchet, was a French mathematician. He made major contributions to general topology and was the first to define metric spaces. He also made several important contributions to the field of statistics, probability, as well as calculus. Pavel Alexandrov, sometimes romanized as Paul Alexandrov, was a Soviet mathematician. He wrote about 300 papers making important contribution to set theory. The Alexandrov compactification and the Alexandrov topology are named after him. George Cantor, a German mathematician, played a pivotal role in the creation of set theory, which became a fundamental theory of mathematics. Between 1868, we find Felix Hausdorff, one of the greatest founders of modern topology, Max Den, who founded that Den twist, and he was a student of the great mathematician David Hilbert, and finally resolved the Hilbert's third problem. L.E.J. Brouwer, who was the founder of modern topology and provided the simplical approximation theorem, and Solomon Lefschetz, who provided the theorem on topology on hyperplane and made contribution on Lefschetz manifold, Lefschetz number, and Lefschetz principle. So this covers more or less a kind of a brief history of topology, the contributors, etc. And now we come back to the most important part of topology, that is what is called a topological invariant. Now, before I go and give you a brief idea about what is a topological invariant, I would like to use an analogy which I used in my general theory of relativity video to demonstrate the same idea of what is an invariant. Now, suppose we are in a flat surface and we get a vector A, and we try to measure the components of the vector as AY and AX, and we measure this by the blue line. And then we plot it on a curved surface. This is X and Y, and this is the curvature. And we try to get the same vector, but you see this red line on the X and the red line in the Y, this gets extended. That is, A prime X is bigger than the original AX, and A prime Y is also bigger than AY. But what happens is that the A prime X being longer and A prime Y is longer, A is invariant. So you see that in the history of study of putting things into different curved manifold or geometry, the concept of invariant is still there and it remains there. Further, as you see that in this kind of a surface, when we are measuring AX and AY, these two, and then we rotate that in a rotated frame and we plot the A prime X and A prime Y. This one is bigger compared to the original and this one is shorter. So what I'm trying to tell you is that this is actually what we need to understand about invariance. And invariance is not only in the concept of topology, it lies everywhere. But before we go into invariance understanding, I need to quickly give you another concept which is called what is a homeomorphism. Okay, so first let us understand on a very layman's language. So homeomorphism is a correspondence between two figures in a one-to-one mapping such that the function and its inverse are continuous. What do I mean by that? So if I get a function which maps between two topological spaces, homeomorphism happens if there are three conditions which are being satisfied. One, f is a bijection. If you don't understand bijection, I've given a kind of a figure. Second, f is continuous. Obviously, it has to be continuous, just like the cup is changing into a donut, and f inverse is also continuous. So sorry. So what we understand is that homeomorphism is something which is a one-to-one correspondence between one object to the other, so that it is bijection, it is continuous, and the reverse is also continuous. So the cup, it turns to donut, the donut also turns back to the cup. That means the inverse is also true. So let me show you further examples. So homomorphism is a continuous stretching and bending of objects. So correspondent between two figures defined by a one-to-one mapping that is continuous in both directions. Now you see, if I throw this arrow in this direction by this green one, it shows that the coffee cup turns into a mug, that is the function, and when it moves from the coffee cup back to the donut, that is the inverse of the function. That means I can tell that this donut is homeomorphic using this sign to a coffee cup, and same is this one. So this is homeomorphic surface. That means the cube can be blown with air inside it to a kind of a sphere, and then finally to a sphere. So now we come to the concept what is called a topological invariant. Now that we have understood homeomorphism, a topological invariant becomes easy. So topological invariance is related to mathematics, which is called a topological property, and that is invariant under homeomorphism. So homeomorphism is something that you have understood, that the function should be continuous, bijective, and the inverse is also true. and that homeomorphism, topological space that is invariant when the homeomorphism occurs is called topological invariant. So that means topological invariants are quantities with topological spaces that do not change under continuous deformations of space. Let me give you a quick example. Now, if this is a proper space X, is a kind of an object, say for example, right? Now, this space X, whenever a space X possesses that property, every space X, when you got this one, this one, this one, this one. So every space A, B, C, and D possesses that property, every space homeomorphic to this space prop, which has. Okay, let me give you further example. If this space X on the left hand side has got a property, then every space which is homeomorphic to that will have the same property. So this property gets transferred here. If this is also there, it will go here. If it is here, it is here, then it will go to here. So property of spaces is a kind of a topological property. If whenever a space, any x, y, z possesses that property, every space which is homeomorphic to that space, that means A is homeomorphic to x, B is homeomorphic to x, C is homeomorphic to x, D is homeomorphic to x, will also have that kind of a property. Let me show you. So if this coffee donut is homeomorphic to the coffee cup, and this one is homeomorphic to the kind of a sphere, then this one will also be homeomorphic to this, and this property will have this will also have here, and this will also have here, and that is what it is the definition. If a set X is equipped with some structure and makes X into a topological space, then by a topological invariant of the set X is understood a property of this topological space induced by the given structure on X. Fairly simple. So we understand what is a homeomorphism: bijective, smooth, and inverse is also smooth, right? Inverse is also true. So that homeomorphism, when we take spaces, that is what is called topological invariant. So topological invariant is something, let us quickly go back again to the definitions so that we can, So in topological invariance is something that invariant is a property of topological space that is invariant under homeomorphism. So when the homeomorphism takes place from space X to A, B, C, D, it will remain invariant and the properties will all be the same. Right. Now, before we go into further discussing more about topological invariant, I would like to show you a Cartesian coordinate demonstration. Now, why I am trying to show you Cartesian coordinate, you will soon understand. Now, suppose this is a simple congruency, side, 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 angle, side, angle, right hand side. We know this from our school days, right? So they are congruent to each other, right, in a Cartesian coordinate. So now if we rotate this, right, if we rotate this and if we get an angle 110 and we rotate that angle, we find that the angles are also congruent even if they are flipped or rotated. I'm giving you a simpler example of topological invariance. So these Euclidean spaces, when you get angles, they're rotated, right, and they're flipped, yet the congruency remains. So the question is that, can we devise a tool where all these polygons, I call it as polygons clubbed together, are invariant under changes? Let us find out. So we group all those shapes into polygons, and what happens is that these polygons get generalized into any shape, and this concept of congruency gets into what is called a topological invariant, and a property preserved is under homeomorphism. So I hope that now it is clear what is a topological invariance, because topological invariance is something where we are taking the same Euclidean thing, right, and we are generalizing it to any shape. So if the polygons get generalized into any shape, that means under homeomorphism it changes, yet it remains the same. And the concept of congruency for angle, side, etc. are now called topologically invariant, because the congruency, in spite of flipping around, if it remains, Here also, when things change under homeomorphism, we have just seen that also remains and the function is preserved, and that is called topological invariance. Okay, so here you see the torus and here it is. So topologically they are the same because bidirectional mapping of one shape to another preserves the notion of points being near to each other. So these things are there, and as you see, all those shapes, polygons and the sphere, torus, Klein bottle, etc. These are topologically they are the same, although they are geometrically different. So that covers the topic of topological invariance. Now, what is most important is that when we deal with topological invariance, etc., we are going towards generalization. That means we are making all the Euclidean, all the shapes that we have learned into something very generic, so that even those things changes, the invariance property remains. Now, what do I mean by generalization? We will find it in this final part of our video. So from Euclidean axioms, we move to topological axioms. What do I mean by that? Throughout the passage of history, we have seen things have become more easier, things have become much broader. Think of those days when we used to handle the big Nokia phones, and it used to just take an in call and call them out, and we are heavily charged. But now consider a mobile phone, how easy it is, and it serves all the purpose, and we are glued towards mobile from morning till evening. So the technology has helped us to change, generalize. Now you serve the purpose of messaging, serve the purpose of calling, video calling, WhatsApp message, reading, writing, everything. So it has become more and more generalized. Mobile is no more a mobile, it serves as a generic purpose. So if you see into the history, Maxwell's equations were generalized into special relativity, considering the 4 dimensions, etc. Similarly, Newtonian gravity was generalized by Einstein using general relativity. Euclidean postulates were generalized using Lobachevsky's hyperbolic or non-Euclidean geometry. Similarly, Euclidean axioms get generalized into topological axioms. How does it happen? So Euclidean space gets generalized into something which is called a metric space. Metric space gets generalized into topological space. And the concept of closeness, distance, points, neighborhood emerges. So the point is that when we are trying to generalize the typical Euclidean axioms of parallel lines, etc., we need a kind of a form that these concepts would be put. And that is basically the target of our next video. So till now what we have learned is the basic idea of topology, history, contribution, etc. But how do we go from one axiom, because we are no longer using Euclidean axiom, we are using it into a different form, into much broader, which is called a topological space. So that's all for this part of the video. So let's just summarize. We got an overview of topology. We'll learn different kinds of surfaces, etc., how they're related, what is orientability, non-orientability, what is homeomorphism, etc. We learn different branches of topology, which branch is helping in what, a brief history and who are the contributors of topology, and then we understood what do we mean by invariant property, both through Euclidean and non-Euclidean. We saw that how the angles, in spite of being rotated, preserve, and that is how it happens. And we also learned the process of generalization, and we are going to learn more about that. We just touched base the Euclidean space and topological space. That's all for this video. I hope you like it. This is just an introductory idea of topology. More are about to come, more complex, more advanced, and most importantly, very interesting subjects and factors of topology. Thank you for watching this video. Do like, comment, and click on the bell icon to get all the notification from Physics Fun students. This is Shaunak signing off, promising you to come back with yet another very interesting video on physics, mathematics, as well as topology. Till then, goodbye and stay safe and stay happy.
Now, you can be a part of our team. You can send your scientific articles, essays, research papers, lesson plans on a particular subject of science. For further details, please write to us at editor@physicsforstudents.com. Stay safe and happy.